Hello and welcome to the first of the lectures in this week 5 of the course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. In the last 2 weeks, we have seen the 3 basic fuzzy logic connectives, that of fuzzy negations, triangular norms, and fuzzy implications. In this week, we will deal with fuzzy relations. Let's begin with a brief recap of classical relations. A classical relation can be seen as a mapping from the Cartesian product of some sets to the set 0, 1. For instance, let's take the set X to be the numbers 1 to 10 and Y simply to be the set 2, 3, 5. Now, we could define the relation as follows. X is related to Y if and only if Y divides X. Now, this will allow us to build a relation on this set. So, you could indicate this by a matrix, in fact a binary matrix. Let's for convenience just only start with the set from 2 to 10. So 2 divides 2, that means we put 1. 2 does not divide 3, so 0. It divides 4, if we put a 1. 3 does not divide 2, so put 0. 3 divides 3, put a 1. Does not divide 4, put a 0. So similarly, from the way we have defined the relation, where we have specified when an X is related to Y, we could indicate it by a binary matrix, and this essentially can be looked at as a mapping from X cross Y to the set 0, 1. We could also look at a relation, classical relation, as the subset of the Cartesian space. For instance, all we need to do, if I call this relation R, then R can be written as a collection of ordered pairs from X cross Y. For instance, 2, 2 will remain in R because 2 divides 2. 4, 2 will remain in this collection because 2 divides 4. Now this is the second component is Y and the first component is from X. Similarly, 3, 3 will remain. 6, 3 will be in this set. So it's a collection of elements from the Cartesian product of X and Y. So in that sense, a relation can be seen as a subset of the Cartesian product. In the case of binary relations, it is customary to write like this. Indicate if R is a relation, X, R, Y, if and only if X, Y belongs to R. Where now we are interpreting R as a collection of elements, as a subset of X cross Y. Now, if the set X and Y are same, in the case of binary relations, if both X and Y are same, then we can come up with some specific or special binary relations. A relation is said to be reflexive if X is related to X itself under the relation for every X. It is said to be symmetric. If X is related to Y, then Y should also be related to X. It is said to be transitive if X is related to Y and Y is related to Z, then X also should be related to Z. Let's spend a few minutes on this to understand that these 3 properties are in fact mutually independent. Towards this end, let's come up with relations having different properties, binary relations having different properties. The domain of the relation X will be clear from the way we are defining it, so we will not specifically write out or specify it explicitly. Now, also note that if now we are looking at R as a X cross X to 0, 1, we know that it could be written in the form of a matrix. If we could list out the elements of X, Note clearly that reflexivity means in this matrix the diagonal becomes 1. Symmetry implies that this matrix is symmetric. Now, what does transitivity mean? Well, it is not immediately obvious, or it cannot be seen from the matrix alone, the corresponding relation, but we'll try to interpret it and see what is inside the definition of transitivity. So now let's begin with defining some functions, some relations having one or more of these properties. Let's begin with a relation which has all of these properties. For instance, if you consider x and y from a set of natural numbers, you could define a relation like this. X is related to y if 3 divides x minus y. Clearly, you could say 3 divides 0. If you allow that, then x is related to itself, it is reflexive. If x minus y is divisible by 3, then y minus x is also divisible by 3. And if x minus y is divisible by 3 and y minus z is divisible by 3, then it is clear that x minus z is also divisible by 3. Simply you need to add x minus y plus y minus z. You will get x minus z. Both of them are multiples of 3. So the addition also will be a multiple of 3. Now what about a relation which is none of these? Do we have such a relation? Quite interestingly, think of it like this. X is related to y only if x employs y. Note that not all relations have to be actually over the set of numbers or mathematical in nature. So if you think of this, a person may not be employed in his own company, so x may not be reflexive. If x employs y, doesn't mean that y also employs x. That's not true, so it's not symmetric. And clearly it is not transitive. If x employs y and y employs z, it does not mean that x employs z, because x could have one company A and y could have another company B, and so x may not be employing z. So here is a simple example of a relation which is neither reflexive, symmetric, nor transitive. Now let's look at relations which have two of these properties. So what could be a nice interesting example for a relation which is only reflexive and symmetric but not transitive? Think of this. X is related to y if x and y speak a common language. So clearly, if you look at this, so we have said x is related to y if and only if x and y speak a common language. Clearly, it is reflexive because x, whatever he speaks, is understood by x himself, so it is common. If let's say that x speaks language A and B and y speaks language B and C, so now there is something common between x and y. If x and y speak a common language, then obviously y and x also speak a common language, which means it implies that x is related to y if and only if y is related to x. But this relation is not transitive. Why? For example, let's see here that x is speaking the language as A and B, y speaks the language as B and C, so there is something common between x and y. Now bring in z, he might speak the language C and D, so that means y is related to z because of C. However, this does not imply x is related to z, because there are no common languages between x and z, assuming that all x, y and z speak only these two languages. So you have such an example here. What about a relation which is reflexive and transitive but not symmetric? An interesting example would be x divides y and x is not equal to y. So x divides y. So now it is clear that x divides himself. so it is reflexive. X divides y does not mean y divides x, so it is not symmetric. If x divides y and y divides z, then obviously x divides z. So clearly, it is a reflexive transitive relation which is not symmetric. Now, what about a relation which is not reflexive but symmetric and transitive? Perhaps you could say x is a sibling of y. So clearly, it is not reflexive, symmetric, and also transitive. Finally, let's look at relations which satisfy only one of these properties. In this case is simpler. You could define a relation which is symmetric but not reflexive or transitive. For example, you can say x is related to y only if x is married to y. So clearly, x is related to y and y is related to x, but x is not married to himself or herself. Similarly, if x is married to y and y is married to z, doesn't mean that x is married to z. So it is not transitive. Now, how do we specify a relation which is only purely reflexive or purely transitive? But this is where we resort to writing them as matrices or relations. Let's consider x to be with 3 elements a, b, c. We want it to be reflexive but not symmetric. So let's put 0 here and 1 here and 0 here. So clearly it is not symmetric. Now how do we ensure it is also not transitive? Now see that A is related to C, and let's make C also related to B, A is related to C, C is related to B. So if it were transitive, then A related to C and C related to B would imply B is related to C. But let's put a 0 here. So clearly, this relation is only reflexive, not symmetric, and not transitive. So this would be a nice example here. What about a relation which is neither reflexive nor symmetric but only transitive? Let's construct one like that now. So clearly, we don't want it to be reflexive. So let's put zeros throughout on the diagonal. We could also, of course, have 1 somewhere. Now, let's relate A to C and let's relate B to A. So B is related to A and A is related to C. So we should ensure B is related to C. And we don't need anything else. So you see here 0, 0, 1 and 0, 1, 0, which means it is not symmetric. It is not reflexive, of course. And there are only 3 pairs in this relation and they ensure it is transitive. So B is related to A is related to C, so B is related to C. A is related to C, C is not related to anybody else, so transitivity doesn't come into picture. B is related to A is related to C, and B is related to C. So the only possible relations are these, and it is transitive. So this would be a nice example here. So as you can see, often we may not be able to come up with a relation expressible in that, not a very simple, easy to explain relationship, but we would, when you actually construct or get some relations, they may satisfy one or more of these properties. Well, based on these 3 properties, we can classify binary relations themselves. If a relation is reflexive, symmetric and transitive, we know it's an equivalence relation. If it is only reflexive and symmetric, it is called a compatibility relation. Okay, with this, let's move to fuzzy relations. Clearly, given a classical relation, how do we make it a fuzzy relation? By expanding the domain to the entire interval 0, 1. So it's a mapping from the Cartesian product of spaces to the unit interval 0, 1. The immediate question is there a need for it? We didn't ask this question though in the case of classical relations, but let's look at it. To understand this, let's look at a graph. So what is a graph? Graph consists of two things, V and E. V is the set of vertices and E is the set of edges relating the vertices. So consider this graph where you have 6 nodes and let's say this is how they are linked. So now if we label them as alpha, beta, gamma, beta, then if you were to write this, since alpha is related to beta, you get a 1, alpha is related to gamma, you get a 1, it is related to rho, you get a 1, alpha is not related to delta, so you get a 0. So now, alpha, whether it is related to itself or not, so if you have a self group, yes, otherwise you should put a 0 here. So you see here, from the graph, if it does not have if each node does not have a self loop, then it is not reflexive. However, what you have is the graph being represented in terms of what is called an adjacency matrix. This clearly is a binary relation, binary classical relation. Binary in the sense of having values in 0 or 1. Now, it is also possible that these weights have these edges have some weights. They could be cost, they could be distance, what have you. They could be any number between 0 and 1 or even any negative or positive real numbers. If these were actually representing weights, then what we would have in this matrix are numbers from 0 to 1. 0, alpha, beta is 0.3, alpha, gamma is 0.4, 0.7, and 0. So you see here, immediately the adjacency matrix of a weighted graph turns out to be a fuzzy relation. That means a relation which takes numbers between 0 and 1. Which immediately tells you that some of the graph operations, the operation that you could do on graphs, can also be seen in terms of the operations that are being performed at the adjacency matrix. And now looking at it as fuzzy relations, perhaps we could bring into play some fuzzy logic operators, fuzzy set theoretic connectives, and related operations to glean something more about this graph. Going forward, we will discuss at least one such thing when we discuss similarity classes soon enough during this week. But for the moment, we clearly see that fuzzy relations do arise quite naturally in many settings. So there is a need to discuss fuzzy relations. If you want to look at them as subsets, clearly this is a classical subset in the case of classical relation, and in the case of fuzzy relation, it is essentially a fuzzy subset or fuzzy set on the Cartesian product of sets. Now, you could also, given a fuzzy relation, you could also consider the alpha cuts, because fuzzy relations are essentially fuzzy sets on the Cartesian products. So if you consider the alpha cuts, what you would get is a binary relation, which essentially means then you are looking at the subset from the corresponding Cartesian product. In this case, what we have indicated is only for the binary relation. And immediately many things come into play. This we will see soon enough. So if you have the level set of this fuzzy relation and you pick some alphas from there, if alpha 1 to alpha n is an increasing sequence, then we know that the corresponding alpha cuts will actually be decreasing in terms of the subset. It means higher the alpha, smaller the number of elements you are going to have in that subset. And you could reconstruct the fuzzy relation once you know the corresponding alpha cuts and the alpha, the level set. This is very much the same as in the case of fuzzy set, because fuzzy relations are fuzzy sets on Cartesian products. Finally, we indicate binary relation, classical binary relation like this: x is related to y if and only if xy belongs to the subset. In the case of fuzzy relations, we simply say that x is related to y if r of xy is greater than 0. That means xy should belong to the support of this fuzzy set. Now, can we talk about these special relations also? Means, can we talk about when a fuzzy relation is reflexive, symmetric, and transitive? In the case of reflexivity, this is how it is defined. We say a fuzzy relation is reflexive if r of xx is equal to 1. Just a few moments earlier, we saw that x is related to y in the case of binary fuzzy relation if r of xy is greater than 0. So it should just belong to the support. So we could also have defined that the relation is reflexive if r of xx is greater than 0. Now such definitions also exist. So it is called epsilon reflexivity. So fix an epsilon greater than 0, arbitrarily small, and say that r tilde is reflexive if this is greater than epsilon for all x in x. Now, if r of xx is greater than 0 for every x, and assuming that it is finite, we could always find an epsilon, which is the minimum of all such possible pair that you can take, and then call that as the epsilon, and it becomes epsilon reflexive. However, in this course, when we refer to reflexivity, it will always be under this definition, that is r of xx is equal to 1 for all x. Now, when do we say it is symmetry? Clear that if x is related to y under the relation to some degree, then y should also be related to x under the same degree. So essentially, the matrix of the fuzzy relation, should be symmetric. The question is, how do we define transitivity? So we know this is transitivity for classical relation. It is not easy to read off whether a relation is transitive or not just by looking at the matrix of numbers. So we need to look a little deeper here. So towards that, let's try and understand what we mean by transitivity here. So transitivity says that if x is related to y and y is related to x, this should insist that x is related to z. Now, in the classical case, what it means is r of xy is equal to 1 and r of yz is equal to 1. This should imply r of xz is equal to 1. But now, here we are only saying that x is related to y and y is related to z. In the fuzzy case, this would mean r tilde of xy is greater than 0 and r tilde of yz is greater than 0. Now what we need to show is that this should imply that r tilde of xz is greater than 0. But we cannot define a fuzzy relation taking arbitrary values, because we know that r of xy is perhaps taking the value alpha 1 and r of y is taking the value alpha 2. So somehow the relation, the strength of the connection between x and z should somehow be dependent on the strength of the relations between x and y and z. Now how do we define this? Now let's look at it. In the classical case, the transitivity is defined only if x is related to y and y is related to z. Now it can happen that x is related to y and y is not related to z, but still x may be related to z, or the other way around. So essentially what we insist here is, if you look at this, we want that minimum of r of xy comma r of yz should be less than or equal to r of xz. So when both of them are 1, then we want this to be 1. If one of them is 0 or both of them are 0, then we really do not care. It does not affect the transitivity. Now this is the definition that we could use also in the case of fuzzy relations. However, notice that x and z may be related through many y's. So that means we essentially take that r tilde of xz should be greater than or equal to all possible connections that can exist between x and z through the different y's, and all we want is it should be max over min of this. And you will see that this definition of transitivity will also hold in the case of classical relationship. So this is typically taken as the transitivity of a fuzzy relation. Why only minimum? We could also use any t norm. So typically it is translated as t transitivity for a given t norm. And you will see that in the classical case, because we are dealing only with zeros and 1, it's exactly the same as the definition of transitivity that we have seen earlier. Now once again, if you look at fuzzy relations, because we have defined these three properties, if a fuzzy relation has all these three properties, reflexivity, symmetry and transitivity, we call it either a fuzzy equivalence relation or typically it is called a similarity relation. If it is only reflexive and symmetric and not transitive, then we call it a fuzzy compatibility relation. These are two very important types of fuzzy relations. Moving forward, in this week, we will see their role in analyzing data itself based on the properties that they allow us to extract from the fuzzy relations. So in this lecture, we have just seen briefly what are fuzzy relations and the need for them, and we have touched upon a couple of special binary fuzzy relations, that of similarity and compatibility. Moving forward, we will look at how to compose such fuzzy relations, the importance of fuzzy compatibility and similarity relations that we have just introduced, the importance of transitivity itself. In fact, a large part of this week, the different lectures that we will have can be seen as elucidating the importance of transitivity of a fuzzy relation and their relationships to many other concepts that readily do not spring to our mind when we are talking about relations. Those are that of kernels and metrics. We will also see how these are related to transitive relations. In the next lecture, we will deal with compositions of fuzzy relations. A good source for the topics covered in this lecture, and perhaps also in the rest of the week on fuzzy relations, is this very good book by George Clear and Bo Yuan titled Fuzzy Sets and Fuzzy Logic. Glad you could join us for this lecture and looking forward to meeting you in the next lecture. Thank you.